Oh yeah, I just realized I almost always start my streams by whistling. So, welcome people. How's everyone? Um, yeah, my name's Zach. If you don't know me, I'm the developer at Gaia Ochos, and today I'm gonna run you through. I just wanna get some of my documents open. I'm going to run you through the functional description of I2C, which is integrated circuits communication protocol. You chat. I need chat. Hello world. Sweet. Okay, cool. Cool. So it looks like chat is working. Looks like everyone is here. Eric, if you don't mind, you can test chat and I can see. Okay, so today the aim for today is kind of just to get familiar with the I2C protocol. What is it? When to use it? Maybe we'll compare it a little bit with SPI, which is a serial peripheral interface, and maybe towards the end we can get into the reference manual for the STM32F1xx CT6 F103C. It's a C6 F103. Anyways, STM F1xx if you want to be general about whichever microcontroller unit we're using. So the first thing we need to do is explore what I2C is. And then after we explore what I2C is, we can kind of now go into looking at I2C in the relevance of this microcontroller that we're using at the moment. Okay, cool. So let's quickly just get a document on the internet. I2C. I think the Wikipedia document should serve us real good, real well. So, I'm not gonna read the other ones at the top, but I2C integrated circuit, pronounced as I2C or ITC. Yeah, is a synchronous multi-bus, multi-master, multi-slave, single-ended serial communication bus. Made by Philips. Okay, cool. So can be found in a wide range of electronic applications where simplicity and low cost of manufacturing is more important than speed. Yes, I2C is not that fast compared to other things, other protocols that we have available. I2C is not that fast, but it does use only 2 pins, and it does already support let's say multi-master environments and also like switching modes. So like it's very easy for whichever device sends a start, we'll get to this, whichever device sends a start signal or a start condition in I2C is therefore it is from that point onwards regarded as the master. So you could have like multi-master configurations. You could have 2 devices and then they could swap which one's master, which one's master, which one's master, which one's master, depending on the operation that you want. Okay, cool. So I think the I2C, yeah, so here's the modes. So I2C comes with a number of modes. Okay. There's standard mode, which is 100 kilobits per second. There's fast mode, which is 400 kilobits per second. Fast mode plus 1 megabit per second. High speed mode 1.7 megabit per second. High speed mode is 3.4 megabits per second, and then ultra fast mode, which is 5 megabits per second. Not all controllers, not all microcontrollers are going to support all the speeds or all these modes, and for that reason you'll have to like you will determine which mode you're going to use depending on the microcontroller and kind of like peripheral or slave that you have, that you need to use in your particular application. Cool. So the thing is, as well as multiple masters and multiple controllers and having multiple speed levels at which we can use, which is kind of the same thing that we did in SPI but using baud rates, I2C has addressing capabilities. So in SPI we were using a slave select line, NSS, slave select line, to select which slave we wanted to kind of communicate with. However, with I2C we have the capability of using addresses. So we have like a 7-bit address, and then like it is an 8-bit packet, but like a 7-bit address where the address is 7 bits, and then you have a read or write bit at the end. We'll kind of go through I2C in like up down. It's a very almost discombobulated approach, but it's a thing like I'm trying to explain everything as I mention it. That way we don't confuse stuff. I'm not assuming prior knowledge of anything, especially with I2C by itself. I'm assuming you know what a microcontroller is, and I'm assuming what you know what a peripheral is and such. But if you do not know, comments or questions or the Discord that's linked in this video down below, you can jump with that and we can talk about this. So yeah. And then another thing that we had in SPI was we did not have how to acknowledge, or rather there was a lot of like, you had to read dummy, you had to send a data, if you needed to read a packet, you'd send a packet and then you dummy read, and then you would read the actual, because every time you sent data in SPI, the data going caused some data to come this way, which could be dummy, which could be not what you want. So you had to like do this dummy read, dummy send thing, which is kind of fixed in I2C with auto arcing and auto knocking. And we'll get to what arcing and knocking is, but basically at the end of each packet, the slave will send at the end of each data packet, the slave will send an arc or a knock, which is an acknowledge that we got the packet, or a knock, which is we did not get the package. And then as well as that, the master can also arc and knock when reading. So the master reads some data, and then it can arc or knock that the read went successful. I'm not going to go through the reference designs and such and who came up with what. I'm just going to go through how this works. So let's look at the types of transactions you can have in I2C. So I2C defines basic types of transactions, each beginning with the start and stop condition and ending with the stop condition. Single message, where a controller writes data to a target. Controller target. Yeah, that's good, new words. A single message where a controller reads data from a target. A combined format where a controller issues at least 2 reads or writes to one or more targets. So this is like a repeated start condition. And we'll get into the reasoning for this later along the line, but I don't need to like read it verbose from the Wikipedia article. But then, so there's a lot of lower level details you can get from this article, but the point today was kind of just to explore what I2C is in this respect. So the next thing, so I2C uses 2 pins, and the 2 pins I2C uses are SCL, or I guess clock, and SDA. So SEL is the clock line, the synchronization clock line, and then SDA is the data line. This is for every clock cycle on SCL, SDA carries some data bit, and that's how we send data. You remember in SPI, this was done by data in or data out on either side of a controller target. Cool. So first of all, we've discovered I2C is much slower than SPI. So I2C would be used where like speed is not a factor, and we want a smaller form factor because we want less pins, and we want like possibly a multi-master environment. SPI is much faster, we have much higher throughput, and you can kind of like basically the fastest SPI can go is kind of determined by the fastest clock you can use, and then I think the least you can divide it by is 2, so there's quite a, you could get like up to quite high data rates. Okay, and then I2C, we've covered that it supports auto acknowledgement and auto non-acknowledges, so that's good. Just I'm gonna pop up in Discord so that we can see if anyone joins and anyone asks any question. So I would like to find a diagram that shows the data moving through. I mean, the timing diagram is also good. Oh, there's a good it's cool. There's a good code example here, but I don't want to do that right now. I just want to find a diagram that shows data moving through, and so that we can kind of like I2C data packet example, because we just want to break down how the data packets is arranged, and then we can kind of like look at them and think about them in same way. This is what we need. So here we can see there's and also this is a good example of how to develop embedded solutions. You basically have to find your own information in bits and bobs in many places. And another thing I'm hoping to show with this live streams is kind of how do you find out the information you want, and then how do you proceed to using the information you want. So if you're going to develop an I2C driver, one of the best things you can do first of all, realize how I2C works in general, have a kind of like a general understanding of what I2C is, and then after you have that and you know all the language that is kind of surrounding this protocol, you can now move over to the reference manual, usually for whichever microcontroller you're writing drivers for, or developing, or even device you're developing for. And then from there on, you can start implementing code, because the code itself, in actual sense, is quite simple. It's understanding what this bit and that bit is doing that makes it a little more difficult. And once you know what those bits mean, you can kind of, it's almost reading, like you can almost read commands. So the standard packet of information in I2C would look at like this. So whichever device generates the start condition, this here, is going to be regarded as a master. So there's no mode, it's who starts the start. Whoever begins the information is going to be the one to be regarded as a master, okay? And then from there on, they have certain responsibilities. And then usually you will have 7, sometimes you will have 10 bits, but in this, for the purposes of this talk, we'll just talk about the 7-bit one, so that it's simple and kind of concise. We don't want to make a 5-hour stream, although that might be something people want, like just diving into I2C. So you have the start condition, which is 1 bit, and then you have 7 bits of an address frame. So start communication, and then I want to communicate with this device determined by these 7 bits. And then what communication do I want? Do I want to read or write? So if you want to read, it's a nil, it's a reset, and then I think I'll have to check this. So read or write is 1 bit. Okay, so this is the kind of packet that you send out. Start communication with this device, and I want to read it or I want to write it. Okay, and then the next 1 bit is sent back by the other device. It's either an ARC or an ARC. So an ARC is I acknowledge, I have matched the address. I am the address that you want to talk to, and I am here. You can talk to me in the way you can read me or write me. And then 8 bits of, say, data frame. Like if you said you want to read, this 8 bit would now be, I think, an address you want to read. Okay. If you said you want to write, this data would be the address you want to write in the slave that you're particularly talking about. And then the next, and then you get another ARC on ARC. And then once you get an ARC, you send another 8 bits. Now this is the data you want to read or write. Or this is the, so if you had said read, this is now the data frame 2 is the data you will be receiving, because data frame 1 is the address in the device that you want to read. Data frame 2 is the data that you are reading. If you wanted to write, data frame 1 is the address in the device that you want to write to. And then data frame 2 is the actual data that you want to read. So say I've got, of which I do, I've got 2 diaries. Okay, cool. And I'm speaking to this 2 diaries through I2C. So I have to say black diary, this is the address frame. So start communication, 1 bit. Black diary, this is the address. And then I want to read into the from the black diary, I would like to read from the black diary. It's very difficult to say that. I would like to read from the black diary. Yo, I need an editor to make like that, one of those ways. I would like to read from the black diary, and I would like to read page 1. The diary goes, I'm here, you can read page 1. I would like to read from the black diary. So the black diary goes, I'm here, you can read me. Cool. And then the next thing I say, I want to read the page on how GPIO interrupts work. Okay, cool. Let's say it goes here. And then the diary goes, hey, yes, I found the page on the I have found the page on GPIO interrupts, and you can read it. And then it spits back the data on that page. And then I go, oh, I got the data, and then I ARC, and then I send a stop bit. I hope that makes sense. Well, for now, let's quickly even read through this article that we found, so we see if maybe we can glean any more. So, start condition. The SDA line switches from high voltage to a low voltage level before the LCL line switches from high to low. So when the SCL is high and the SDA goes from high to low, that's a start condition. Stop condition. The SDA switches from low voltage to high voltage after the SCL line switches from low to high. When the SCL line is high and SDA goes from low to high, that means that's a stop condition, so stop writing. Read or write bit. A single bit specifying whether the master is sending data to the slave or requesting data. So reading 0, writing 1. ARC bit. So if address or data frame, ARC bit is returned to the sender. Okay, cool. So we send an address, we send an address, a read or write bit, and a data frame, and you see, so as you can see, steps of I2C communication. Okay, master sends a start condition to every connected slave. Cool. Master sends each slave bit the 7 or 10 bit address that it wants to communicate that one of the slaves is going to match. So if master sends read or write 101.1.0.1.0.1.0.1.0. So 101, this address is 011, not you, 100, not you, and then this address is 0.1.0.1.1.0.1. Cool. This is the address that we want to talk to. So this is the address. This is the address matching. Each slave compares the address sent from the master to its own address. So each slave goes like, am I this one? Am I this one? Am I this one? No. So slave 3 matches here. Master sends the data. Master sends or receives the data frame. So now slave 3 is matched. Now if I send data, it will go to slave 3, and this is all the data lines are like, this is clock lines. So slave 3 is actually getting data here, we can see. Okay, cool. So after each data frame has been transferred, the receiving device returns an ARC bit to the sender. So yep, not an ARC bit, not an ARC bit, ARC bit. Slave 3 sends back an ARC bit. To stop the data communication, the master sends a stop condition. Cool. No data, stop condition, boom, and then cool. So we won't look at multi-master stuff at the moment. It's the same, it's just a bit of thinking ahead. Cool. So let me go back to my notes. Wait, 10:30. Cool. Mondays are hard for me. I have swimming in the morning, so I'm usually very tired, and sometimes on some special occasions I have racing on Sunday and swimming in the morning on Monday, and that makes me really tired, and today is one of those. I came fourth in my BMX race yesterday. Not good. Very good though, considering it's my third race, but also not good. Okay, so we know kind of how I2C works. Let's say some advantages and disadvantages, and then we'll move on to something else. So only uses 2 wires, supports multi-masters and multi-slaves. ARC and NAC bits can be automated and give confirmation. Yeah, and then hardware is less complicated than UART or say SPI. It's a very well known and widely used. Disadvantages: slower than SPI. Size of the data frame is remember, in SPI you have a 16-bit or 8-bit data frame. As usual, because this is only 2 lines, we need more. There's more hardware to synchronize to make S2C work the way we want. Okay, cool. So we've looked at what the traditional data packet looks like, and we know that. Let me check for some questions or messages on the some messages, and then I'll get back to you guys. Trying to see if anyone is asking any questions. Cool. Let's go to the next thing. So now we have described how start and stop conditions work. Yeah. We have described how addressing works. We have described how arcing and knacking works, and I'm trying to think if there's something that we need to kind of cover before we briefly look at the reference manual. I'm trying to see, do we need to cover anything else? Anyone with any questions there? Not really. Cool. Let's now jump into the Bluepill reference manual, and then we can kind of start from there. I2C, that's where I was. Cool. So I2C introduction, we've done this. Yeah. This is mostly all the stuff we've covered. Parallel bus, multi-master capability, master features, clock generation, start and stop configuration, generation, programmable I2C detection. So this is like the features of this driver itself, of this device itself, and what you can do with it. Just a moment. Okay, let's go. Sorry about that. Just needed to handle something. Okay, we have a functional description. In addition to receiving and transmitting data, this interface converts it from serial to parallel and format and vice versa. So this is all kind of lower level stuff. If you're concerned about how the electronics of the board works, this is kind of good to know, and you can go into like deeper stuff, mostly the data sheet actually, to know more. So communication flow. In master mode, the I2C initiates a data transfer and generates a clock signal. A serial data transfer always begins with start condition and ends with a stop condition. Both start and stop conditions are generated in master by software, by us. When it says by software, it means you're the one who has to generate them. Okay. In slave mode, the interface is capable of recognizing its own addresses. It will match the address. So this thing, you remember this thing? Remember this thing here? When it sends an address to everyone, this address, in slave mode, our device can do that. Our STM32F1 can do that. Bluepill can recognize its own address. The general call address detection may be enabled or disabled by software. So we can make it so that we can just get we can match all the addresses and such. Data and addresses are transferred as 8 bits. MSB fast, the first byte following the start condition, contains the address in 7-bit mode and 2 in 10-bit mode. 1 in 7-bit mode and 2 in 10-bit mode. The address is always transmitted in master mode. 9th clock pulse follows the 8th clock cycle of a byte transfer, during which the receiver must send and acknowledge. So the receiver sends and acknowledges by pulling the SDA line low when the SCL line is high, which is what we can see here. See? So this low here, this acknowledge here, is coming from the slave or target device, not from the master. So it could come from the master if this is a read operation. If the master successfully read data, they could pull the SDA line low. Cool. So we can look at, so main differences here. We're not really going to look at this pin because we're not using, that's SM bus. We're not covering that here. SDA line, SCL line. We have some filters. We have from clock control here, we can determine how fast to use it, how fast to go and stuff. And you can see clearly we have like some control registers, CR1, CR2, and some status registers, SR1, SR2, which you can use to handle configuration, and also we can handle like interrupts and such when we get there. SDA line is connected to the data register, and you'll notice that in I2C we only have one data register, as opposed to SPI where we had like a transmit buffer and a receive buffer. So like all the data goes through one data register. Much easier, much simpler to use. Now this is kind of like how it works. So we can actually read through the functional description paragraphs, because this is what we're going to come back to when we start implementing. So it's good to know this information. By default, the I2C interface operates in slave mode. To switch it from default slave to master mode, a start condition generation is needed. So If you just use I2C, it will assume it's a slave and it'll probably go to the default catch-all address. But if you generate start condition, you will be considered the master. And then you can obviously choose what speed, 2 megahertz, 4 megahertz, and as soon as the start condition is detected, the address is received from the SDL line and sent to the shift register. Then it's compared with the address of the interface or R. So you start it in I2C in slave mode, it will collect 7 bits from the SDL line and check if it, am I the one who's being addressed. The interface ignored it if the address does not match. If the header is matched, the interface generates an ARC. If address is matched, the acknowledge pulse is sent. The address bit is set by hardware, and an interrupt is generated if the bit is set. IT event FN. So I don't know what that IT event is, but let's look at it quickly. IT event FN. So receive buffer not empty, transmit buffer not empty. Yeah, so that's probably the IT event. You basically are sending something or not. Okay, cool. So let's go back to see introduction, reception in slave mode. Yeah, so and then address is matched, and then okay. In 10-bit mode, after receiving the address sequence, the slave is always in receiver mode, it will enter transmitter mode. So slave transmitter, following the address reception, after clearing a DDR, the slave sends bytes from the DR register to the SDL line via the internal shift register. So here it is. Slave, 7-bit slave transmitter. Address, start, address, ARC, and then some event 1, event 301, and then data. We send data, ARC, data, ARC. So this is basically handling EV1 address equals 1 cleared by SR1 followed by reading SR2. EV31 TXE shift register empty, data register empty, write data in 1, TXE1. So all of this will make more sense as we now actually do the implementation, but we know this is how it works. And slave receiver, following the address reception, after clearing the address, the slave receives bytes from the SDL line into the DR, the data register via the internal shift register. After each byte is received by the after each byte, the interface generates in sequence an acknowledge pulse, and then RxNE bit flag so that we can use it. Closing slave communication. After the last data byte is transferred, a stop condition is generated by the master. The interface detects this condition and sets the stop F bit and generates an interrupt if the EVFN bit is set. Okay, I2C in master mode. The master mode is selected as soon as the start condition is generated on the bus with a start bit. The following is the required sequence in master mode. Program the peripheral input clock I2C CR2 register in order to generate correct timings. Configure the clock control register. Configure the rise time register. Program the I2C CR1 register to enable the peripheral. Start the start bit in I2C register to generate a start condition, and then the peripheral input clock must be at least 2 megahertz in SM mode, 4 megahertz in FM mode. SCL master clock generation. The CCR bits are used to generate the high and low level of the clock, starting from the generation of the rising and falling edge respectively. So there's CCR bits that we need to use. And if the SCL line is low, it means the slave is stretching the bus, and the high level counter stops the SCL line being, like slave can be like wait. It can hold the line and say wait. So there's bus stretching. There's a concept called bus stretching, I2C bus stretching. I2C bus stretching. An I2C master controls the clock speed and provides the SCL on the line. It is possible for the slave to device to stretch or hold the clock and alternate the data or commands transmission from the master. Clock stretching is mainly used to hold the master device while the slave is swapped. So if the slave is busy, it can hold the master and tell the master to kind of wait before they go on. Make sense? Let's go back to our document. Setting the start bit causing the interface to generate a start condition and switch to master mode. MSL bit is set when the busy, so once it goes like this. I have some notes here. Once the start condition is generated, bus is considered busy, so no one else can generate another start condition. And then bus cannot be taken over by another master. And the bus is busy until a stop condition is generated. Once a stop generation is generated, the bus can be taken over by another master. Unless, if you don't want to generate a stop condition, you can generate a repeated start condition. This is like holding the line from the master side, and then you can use it. Okay, cool. So slave address transmission. The slave address is sent over the SDA line, and then we have the add 10 bit is set by hardware and an interrupt is generated. So on the other side, so the other bit is set by hardware and an interrupt is generated if the ITVFN is there. So in 7-bit mode, one address byte is sent. As soon as the address byte is sent, the other bit is sent by hardware and an interrupt is generated. Then the master waits for the read of the SR1 register followed by a read of the SR2 register. Okay. The master can decide to enter transmitter or receiver mode depending on the LSB of the slave data, slave address set. In 7-bit addressing mode, to enter transmit mode, a master sends the slave data with LSB reset. To enter receiver mode, with LSB reset. To enter receiver mode, the slave address with LSB set. Least significant bits. So we'll look at this. Master transmitter. Following the address transmission and clearing. I mean, I'm reading this in prose because I'm reading this in a live stream, but I would advise to read this in detail as much as you can and go to all the like little abbreviations and such. I've done this before to prepare for this stream, so that's why I'm not doing that. But it's good to read the whole thing, and then at some point you will get to looking at the registers, and it will be very easy to read the registers and decide this is what you want to do. So because we've gone through receiving and transmission, I think we can now, all the other parts are kind of just shifted, and we'll explore them as we're writing the code. So what I want to do as a kind of finishing of this is look at the I2C registers and where to find them, and then we can kind of come up with an assignment. So there's an I2C CR1 register. It's a 16-bit register. It's used for there's an acknowledge enable, stop generation, start generation, no stretch, general call enable. This is like, if we get any message, it's ours. ARP enable, PEC enable. This is all data. Some of this I used for the SM bus, which we would be using. Okay, cool. So control register 2, there's DMA. We don't need it right now. DMA, not right now. Buffer interrupt enable, we're probably gonna use that. Event interrupt enable, we're probably gonna use that. Error interrupt enable, we're probably gonna use that. Frequency, we're gonna use that to set the speed. On address register, we're gonna use that when we want to use the current device as a slave. And on address register 2, we're probably also gonna use that. Data register, this is when we want to send. So we can put data in here or read data from here. This is when in receiver mode, we read data from here. When in transmitter mode, we put data here. Status register, SMB alert we're not using. Timeout we probably will use. PCR will probably use. OVR will probably use. F will probably use. And bus error will probably use. And then there's this status, I think this is SR2. No, TXC, RXNE, stop F, add10, BTF. So, address and start with. Cool. And then there's status register 2, packet error, dual flag, SMB host, SMB default, general call, transmitter receiver, busy, MSL. So, and then there's clock register control, which is to set the speed, and we're gonna use that for sure. Time to rise, we probably will use that. And then there's the register map at the bottom. So the first kind of thing I would do is I would go into our code. And the first thing we need to do is we need to do the bit definitions so that everything works. So let's go to drivers, and I think we'll start in the include, and we'll start in the header file, in the MCU specific header. First thing we need to do is probably add I2C. I believe I2C is in APB1, so we need to add I2. Oh, there you go. Already added it. I2C, add I2C to your APB1 peripherals, and then we'll probably need to add I2C register definition, this one. So this register definition for I2C would look like this. So these are the CR1, CR2, OAR, OAR2, data register, status register, status register 2, so CR, time to rise. We need to add that, and then we'll probably need to add addresses for I2C here, and then we'll need to add some clock enable for I2C and disable for I2C, and then we'll need to add some interrupt request numbers here for I2C. This is already done, this is already done, and then we'll need to add, it's easier to read the code when you add our bit positions. So the other thing we'll need to do is do our bit positions. Once we do all of this, we can start implementing. So I'll leave that as kind of like the quest for this vlog. I really did want this to be the first ones when we deal with the protocol first. The first thing we're going to do is just explore it and understand it, what to do, where to do, how it works, how it goes, and then after that we can kind of now start breaking down the protocol and actually writing code. So I think it's good to kind of go out, populate the MCU specific header with the data that we need. So it's going to be I2C register definition, clock enable, all the stuff that is in here that is generic. This is not like functioning. And then the I2C bits. Once we have all of those in, we're ready to now go back and implement stuff. So thank you so much for coming to today's short stream. I wonder if anyone has any questions. For I2C. You can send them in the comments below. If anyone's in the chat now, I don't know who's on live now, you can also post your questions on the chat or on the WhatsApps where I've been posting like when I'm going live. I don't see anyone. So cool. I don't see any questions at the moment. That was good. A brief introduction into what the STM32F1xx I2C will look like. The task now would be to add all the kind of meta information that we need into our MCU specific header, and then from from Wednesday, next stream, yay, Eric's here. From Wednesday next, we can start doing some code implementation. But at the moment, yeah. So add I2C register definition here, and then add some port addresses. I think we have like I2C port addresses. So add define the APB. It's gonna be APB1. So we need to define APB1, AHB, APB2. Is there somewhere? Yeah, somewhere here. Yeah, we should probably move this down so it's below the register definitions, or move this up so it's before them. And add clock disables for I2C and clock enables, and then I think add register reset macros, add IRQ numbers for I2C, and then add the bit positions for the, you could do all the registers, but I'll probably like choose some registers by on Wednesday, so that we just put in the ones we want. But usually KIMSYs or the other libraries that come from the vendors, from the silicon vendors, usually include all the bits. And eventually our drivers are going to cover everything on the MCU. So eventually we will add all the bits. Yeah, no questions right now. I don't see any questions on Discord. I don't see any questions on WhatsApp. I don't see any questions on YouTube. So I'm going to choose to stop the stream here. And on Wednesday we start writing code for I2C. I'm really glad to get here. Thank you all so much for coming, and this has been amazing. Once again, I'm Zach from Gauchos. See you guys. Cheers.